We're so used to the natural numbers, namely the numbers we use to count things in our everyday life, and it seems as if we've never questioned their origins or validity, not to mention the addition or multiplication of two such numbers. We do not think about it, but can still add and multiply whenever needed. These numbers just sort of are there from the very beginning, and it seems odd to even question their existence. In this short video, I would like to show how we can formally construct the numbers we count with and proceed to even add and multiply them by using a few underlying axioms and sets, which will be defined in a second. But firstly, I would like to mention that basic knowledge of set theory might be useful, so don't be disappointed if not everything comes naturally. In this video, we'll cover the definition of a set, the von Neumann construction of ordinals, definition of a successor function, we'll construct the natural numbers, define addition and multiplication for two natural numbers, we'll briefly cover functions, and end up with a conclusion. Let's start with a definition of a set, which underpins most of our future work in this video. Set is a collection of different items. The word different here means that there can't be two identical items in a set. It is denoted with two curly brackets, and elements of it are written in between them, separating them with commas. It is also important to note that the order does not matter, so the following sets are equivalent to each other. Other examples include a set of emojis. It can also contain some random symbols, or even other sets, or even sets and symbols put together. It can truly be anything. What it can't have is duplicate elements. Since not all of the elements are distinct, this would not be considered as a set. The definition says that it only has different items, hence this is not allowed. Instead, we discard the repeating items and rewrite the set without them. One of the most important sets is the empty set, denoted by the two curly brackets or the symbol on the screen. It is simply the set that has no elements in it and will prove useful later on, so keep that in mind. Finally, among many operations that could be used to manipulate sets, one of them will be needed later on, which is the union operation, defined on two sets as follows. Take sets A and B with the following elements. Then, the union of them, denoted as follows, is simply the set with both of their elements put together. Now, for a more complicated example, take these sets. The union of them contains all the elements that are different taken from each of the sets, and even though C repeats itself in both of them, it is included only once in the union. Now, by having this basic definition in our toolbox, we can start making sense of numbers, forget all of the current knowledge you have about them, and follow along. Let's consider the so-called von Neumann construction, which is a way to construct numbers by using only sets. For starters, define a number which we call 0 as the empty set, meaning a set with no elements. Define our second number, call it 1, to be the set containing 0. You can also write it purely in terms of other sets, since we know what 0 is from before. Define our third number and call it 2, to be the set containing numbers 0 and 1 as elements. This can be written purely in terms of other sets as well, since we have already defined them above. Now, the same holds for our fourth number, call it 3, and let it be the set containing 0, 1, and 2, which can also be expressed purely in terms of sets. Try to really understand that all it is a set of sets of sets of sets, nothing else, and it is unique for this number that we call 3. Also, this can be extended to other numbers as well, but for an add, we need more tools. It is time to define the successor function. To help our intuition, we can describe the successor function as a function that, given a number, outputs the next number after it, namely increments it by 1. Formally, this can be defined as follows. The successor function, denoted as capital S, given a number n, produces another set, which is the union between the number n and the set containing it. We call that number the successor of n. The first number that we got to know was 0, so let's take it to be n at first. The successor of 0 is the union between 0, which is the empty set, and the set containing 0, which outputs the number 1 as we have defined it previously. Let's do this for other numbers that we know from before. For n is equal to 3, we have a number that we have never seen before. Let's call it 4. It's the authentic set containing 0, 1, 2, and 3. To reiterate, it is easier to think of the successor function as adding 1 to the number, but we don't yet know what addition is, so we should only use this to help our intuition. Now we have the tools to construct the set of all natural numbers, in other words, the set of all numbers that we simply use to count things. Again, let's abstract on the successor function to make it easier for us to grasp, but don't forget that only sets are being used under the hood to describe each of the numbers. Consider the number line. It stretches to infinity, but let's constrain ourselves with the numbers up to and including 10. If we start applying the successor function from 0, we can see that we are constantly moving along the number line. Hence, the fact that we can describe any natural number by only incrementing the previous numbers by 1 seems intuitive. Before we formalize this, don't forget that any number on the line can be written as a successor of a successor of a successor, and so on. It's time to define the set of all natural numbers formally. Let's look at the following 3 statements, which we call axioms. We take them for granted and use them as our building blocks. Consider the set X such that 0 is an X, if some number n is an X and the successor of n is an X, and finally, X can contain an infinite amount of elements. From the first 2 statements, we get the following. Since 0 is an X, the successor of it, which is 1, must be in X, but then 2, 3, and 4, and so on, must be in X as well. We also have the third statement, which allows for an infinite set to exist. Hence, we get that X is an infinite set of numbers, which we call the set of all natural numbers. The following is the set for some small portion of natural numbers to visualize. Finally, let's see what it looks like to have a set of all natural numbers up to 24 and included, expressed purely in terms of elementary sets as we have seen before. And there you have it. Now we have the set of all numbers represented only using sets up to and including 24, which looks like this. The problem is that this is only all of the numbers up to 10, and it still looks a lot. As a matter of fact, the number of characters to represent the natural numbers grows exponentially. Hence, for numbers up to and including 24, it would take tens of millions of characters to represent. You can see it here. What's next is addition. For natural numbers, we can define addition using a concept called recursion, where we break down a larger problem into smaller, simpler parts. Here's how we approach this. Let's start with a simple case. If we take any natural number a and add 0 to it, the result should be just a itself. This makes sense because 0 represents nothing, so adding it does not change a in any way. Moving on to another case, which might look a little strange. Here we define what it means to add a to the successor of another number b. To make this definition work, we use recursion by relating it back to something simpler. This equation says that if we want to add a to the successor of b, we can think of it as taking the successor of a plus b instead. This way, we break down the problem of adding a to the successor of b into a smaller problem of adding a to b itself. This recursive definition ensures that we can always reduce the addition of two numbers to the addition of some number with 0, which we know to be the number 0 itself. Let's see this in action. Consider adding 2 to 3. We first transform 3 to the successor of 2. We then apply the second property. Now we can transform 2 to the successor of 1 and apply the second property again. We finally transform 1 to be the successor of 0 and apply the second property for the final time. Here we eventually use our first property and transform the successor mass into the number 5, giving us our answer. This can be confusing at first and sort of magical that these two rules actually work together to give rise to the addition that we know of. We can also define multiplication in a similar recursive manner. Let's start with a simple case. If we take any natural number a and multiply it by b, the result is simply 0. This makes sense because multiplying anything by 0 represents taking 0 copies of that number, resulting in nothing. Next, define a multiplied by the successor of b to be a plus a multiplied by b. This recursive rule reduces the problem of multiplying a by the successor of b to the simpler problem of multiplying a by b and eventually by 0, which we know to be equal to 0. Let's see this in action. Consider multiplying 2 and 3. We firstly notice that 3 is the successor of 2 and use the second property. We then proceed to use the second property a couple more times until we get multiplication by 0. And here we can use our first property. We finally get our answer, which is 6. It is important to note that we can take the addition of two numbers for granted here, and we do not go deep into the calculations of them. Finally, let's quickly take a look at addition and multiplication abstractly. We can think of them as functions, each taking as input two natural numbers and producing another natural number as an output. One way to visualize this is to imagine addition and multiplication as machines that, whenever given two natural numbers, outputs another one after following a given set of rules. To summarize, we started with the notion of a set and tried to build numbers from scratch using them. We proceeded to define the successor function to make the definition of other natural numbers easier. We then quickly introduced 3 axioms and leveraged them to define the set of all natural numbers. We proceeded to define addition, which didn't seem intuitive at first, but certainly aligns with our everyday life calculations. We then defined multiplication as repeated addition. Eventually, we ended up describing what addition and multiplication are in terms of functions. There is a lot more underlying stuff, and some of it will be addressed in the future video.